So today we're going to learn Newton's laws of motion from statics to dynamics. We've learned that in kinematics, we describe motion through displacement, velocity, and acceleration. But today we're going to learn how the forces are related to motion. In history, Aristotle has said that an external force is required to keep a body in uniform motion because he saw that when he pushes the ball just moves forward. And then when he stops pushing it, the ball will stop at the end. But this is an intuitive but incorrect view that dominated for 2,000 years. Then Galileo has done an experiment that he found that no force is needed to keep an object moving at constant velocity. Because he realized even if you are not pushing the ball, it still moves forward for a while. Yeah. So he recognized that objects slow down due to friction, not lack of force. Because what he did was a thought experiment with an ideal slope. The ideal slope has little friction. He found that if he put the ball here and released it, the ball will always go to the same height in the other end. And then he let the slope on the other hand very close to horizontal. Although the length of the slope changes, the ball still reaches the same height. So he thought that what if the slope is very horizontal and the ball will always move in order to find that same height. Yeah? So this is the foundation for the Newton's first law. It states that an object at rest remains at rest, and an object in motion remains in motion at constant speed and in a straight line, unless acted on by an unbalanced force. It is also called the law of inertia, that the natural tendency of an object to resist changes in their motion. You can say that resist changing motion, or you can say to maintain its previous motion. So the force is actually the cause of the change in motion, not the cause in motion itself. And when there's no net force on the object, it means there's no acceleration. We've learned that the definition for acceleration is the rate of change in velocity. So if the acceleration is zero, then the change in velocity is zero. That means the object will remain in equilibrium, depends on its previous state. So if it's at rest, then it will remain at rest. But if it was moving, then it will change to constant velocity when there is no force on it. So the measure of inertia is related to the object's mass. The mass is not just how much stuff an object contains, it is also the quantitative measure of an object's inertia. The greater the mass, that means the inertia is greater, which means it's harder to change the object's state of motion if it's with a larger mass, and it will accelerate slowly with the same force compared to small mass. And what if there is net force? Then how will the object move? So we come to Newton's second law. It states the relationship between the acceleration, the force, and the mass. So the acceleration is proportional to the net force, which means when mass is constant, doubling the force will double the acceleration. And also, since the mass is related to the inertia, and the greater the mass, then it's harder to change the object's motion, which means the acceleration of the object is inversely proportional to the mass. So when force is constant, doubling the mass will cut the acceleration in half. So the acceleration will become 1/2 of its previous value. So we can say that the net force equals mass times the acceleration, and we can rearrange this formula into A equals net force divided by mass. So we can say if the net force is greater, then we have a greater acceleration, but when the mass is greater, the acceleration will decrease. And we can see this example. So when an object of 2 kilograms on a horizontal surface, we can first draw the free body diagram. It's 2 kilograms. And there is a pulling force of 4 Newton. Friction, 2 Newton. How to calculate the object's acceleration? So we know that there's only 2 forces, but they're in opposite direction, so the net force becomes 4 Newton minus 2 Newtons, so it's 2 Newtons. And acceleration equals net force divided by mass, so we have 2 Newton divided by 2 kilograms, and then we get 1 meter per second squared. And how to find the velocity at t equals 4 seconds? We've learned the formula, the equation for the uniform acceleration. The final velocity equals the initial velocity plus a times the time. So we have the initial velocity is 0, the acceleration is 1 times 4 seconds. So we have the final velocity is 4 meters per second. Okay. Then we can see the Newton's third law. It tells us the relationship between action and reaction. So for every action force in nature, there is an equal and opposite reaction. For example, if the object A pushes object B, the force of A on B is FAB. And at the same time, there will be a force of B on A, so we can say FBA. And since these 2 forces are in different direction, or they're in opposite direction, so we can say if we set the right as positive direction, then the left will become the negative direction. So we have FAB equals minus FBA. From this equation, we can know that these action and reaction forces, they have equal magnitude, opposite direction, and pay attention to the object that the force exerts on. They are the different objects. So we can compare this Newton's third law pair force with the balanced force, which helps to keep the object in equilibrium. For example, if there is a book resting on the table, then there is a gravity or its weight, and there is a normal force. These 2 forces act on the same body. They are the balanced forces, and also they are not the same type of force. Because the normal force comes from the pressure that the book puts on the table. And when the table has a deformation, it wants to return to its original shape, so it will have this normal force on the book. But the weight comes from the attraction between the book and the earth, since both of them have the masses, so they will have the attraction. And let's come back to the Newton's third law pair. Its characteristics are equal magnitude, opposite direction, they act on different bodies, and also they are the same type of force. So these are the 4 characteristics of the action-reaction force pair. Okay. So now we can have a synthesis of these 3 laws united. So the first law tells us about the inertia, the states of motion. It establishes that the baseline, the object resists change in motion when there is no net force, and this means there is no acceleration. And the second law, it tells us the dynamics, how an object changes its motion by forces. So it qualifies the change. If there is net force, it will cause acceleration, which is proportional to mass. So we have the net force equals mass times acceleration. And for the third law, it tells us the interaction between mutual forces. It ensures the consistency that force always occur in equal and opposite pairs. So we have FAB equals the minus of FBA. And also they act on different bodies and they are the same type of forces, okay? So together they form the foundation of classical mechanics. And now we can see this practice problem 1. When an object is at rest on a horizontal table, which statement correctly describes the forces? The choice A said the support force from the table and the object's weight are an action-reaction pair. We've learned that these 2 forces are not the same type of force, and also they act on the same body, so it cannot be action-reaction pair. And choice B said they are balanced forces that can cancel each other. Well, that's right, because they are the same. Both of them are 100 newtons and they act on the same body, so they are balanced. It helps the object to keep in equilibrium. And choice C said the object has no inertia because it's not moving. Well, the inertia is the property of an object. As long as the object has the mass, it will have the inertia, no matter whether it's moving or not. So it's wrong. And choice D said that the support force is greater than the weight to keep the object stationary. No, they should be equal rather than greater. Okay, so we choose B here. And let's see this practice problem 2. You may pause for a little while and then you can check with the answer. Okay, so we have the object with mass of 10 kilograms rests on the horizontal surface. The coefficient between the object and the surface is 0.05. A force of 10 newtons is applied to the object. What is the acceleration of the object? So first, we should have this free body diagram. It's 10 kilograms and there is a force of 10 newtons applied, and also there is a frictional force, but we have to calculate this frictional force at first. So we have the friction force equals mu, which is the coefficient of the kinetic friction, and times the normal force. And here the normal force equals its weight, so mu mg. So we have 0.05 times 10 kilograms times, we use the acceleration of free fall as 10 here. So we got the friction force is equal to 5 newtons, which is smaller than the applied force. So the object will move with an acceleration. And we have the net force is 10 newtons minus 5 newtons, so we got 5 newtons. And then the acceleration equals the net force divided by the mass. It's 5 newtons divided by the 10 kilograms. So we have the acceleration is 0.5 meter per second squared. So we choose D here. Okay. So let's take a summary of the whole class. So we've learned that the inertia is very fundamental. The objects will naturally resist the changing motion. And if there is force, it will cause the acceleration rather than the motion itself. Because if there is no force, it might at rest, but it also can be the state of constant velocity. And the quantitative link between the net force and acceleration is F equals mass times the acceleration. They are mathematically connected, so we can have the precise prediction of motion according to this formula. And forces, they are interactive. Every force there is an equal and opposite reaction force, and they always occur in pairs. Also, they are the same type of force acting on different bodies. And since we learned these laws, we have the foundation for the understanding of energy, momentum, and rotational motion in the future chapters. So thanks for your attention.